In this module, we are going to define the efficient frontier for a mean variance portfolio selection problem. We are going to walk through how to compute the efficient frontier for a 2-asset market and then for a general D-asset market. And the main punchline is that the D-asset market is no different from a 2-asset market. If you remember, what we said was for a given level of risk, the efficient frontier gives you the maximum possible return. So this is the efficient frontier. This particular point corresponds to the return of a portfolio which is an efficient portfolio, or it's a frontier portfolio. All of these things are synonymous. It's a portfolio that for a given level of risk gives you the maximum return, or another way to look at the same point is that for a given value of return, this portfolio gives you the minimum risk. So any investor wanting to hold a certain amount of risk or wanting to hold a certain amount of return will want to be on this efficient frontier. And in this module, we're going to walk you through the calculation of how this particular curve is computed. We're going to work with a very simple example first, just of 2 assets, 2 risky assets, and then in the later part of the module, we'll show you that that is the most general. In fact, if you have any number of assets, you will end up using only 2 mutual funds to construct the efficient frontier. So here's my problem. I want to do mean variance optimal portfolio selection for a 2-asset market. Asset 1 has mean return mu1, it has variance sigma 1 squared. Asset 2 has mean return mu2 and variance sigma 2 squared, and the correlation between the 2 assets is rho. What's nice about a 2-asset market is that the portfolio constraint is very simple to write. A portfolio, remember, was the fractions invested in the different assets. So in a 2-asset market, there's only one unknown x. Suppose x is the fraction that you invest in asset 1, then 1 minus x will be the amount you will invest in asset 2. And therefore, the return of this portfolio, x 1 minus x, is going to be the mu1 times x, because that's the amount that you invest in asset 1, mu2 times 1 minus x, because that's the amount that you invest in asset 2. What is the variance of this portfolio? It's going to be sigma 1 squared times x squared. That's the variance coming from asset 1. Sigma 2 squared times 1 minus x squared, which is the variance coming from asset 2, plus 2 times rho sigma 1 sigma 2. And if you go back, this is nothing but the covariance sigma 1, 2 between the 2 assets, times x, the amount invested in asset 1, times 1 minus x, the amount invested in asset 2. It's very simple. It's one-dimensional in the sense that the only unknown is x, and that's why 2-asset markets are very easy to describe. So I want to solve minimize risk formulation for the mean variance portfolio selection problem. So what I want to do is specify a target return and then find a portfolio that achieves the target return but has the minimum risk corresponding to that target return. This is the return of the portfolio. This is mu of x. We wanted that to be greater than equal to r. Here we are saying that this is exactly equal to r. So there's a difference between these two. We wanted it to be greater than equal to r, and we are now wanting it to be equal to r. The reason we made it equal to r because it's very easy to compute. One equation, one unknown, I can solve for x. I can plug that x into the expression for the variance, and I'll get the efficient frontier. But this fact that I want it equal to r will come and affect us in the final solution, and we'll have to reinterpret what that means. So for now, let me erase all of this so that it becomes clearer what we are trying to do. What we are saying is, among all those portfolios that give me a return exactly equal to r, find me one which has the minimum variance. For a 2-asset market, this becomes trivial because there's only one unknown x, and I can solve for it. So there's only one portfolio that gives me the desired return r. And what's the value of x? It's simply r minus mu2 divided by mu1 minus mu2. You simply solve this one-dimensional equation and you'll get the answer. So I know the portfolio x that is going to give me the target return. I'm going to plug it into the expression for the variance. So if x is r minus mu2 times mu2 minus mu1, 1 minus x, which is the amount that you invest in asset 2, is going to be mu1 minus r divided by mu1 minus mu2. You can just do the algebra and it'll turn out to be right. So what I've done in this line is that here I've just said x, so it's sigma 1 squared x squared. Here I put in 1 minus x, so it's sigma 2 squared, 1 minus x squared. This is x, this is 1 minus x. If you plug in the answers, you'll exactly get this expression. If you expand it out, you'll end up getting that sigma r squared is ar squared plus br plus c. So these are just numbers that depend on sigma 1, mu1, and rho, and sigma 2, mu2, and rho, and so on. But these are numbers. R is the only unknown. So what does this tell me? It tells me two things. If I know the target return R that I want to get to, the variance, the minimum variance corresponding to that target return is explicitly given by a formula. In fact, it's given by a parabola. So what am I drawing here? I'm taking a value of R, and how was this computed? I plugged this value of R into that formula. I calculated out what sigma R squared is going to be, took a square root of that, that's going to be volatility. So I'm plotting R in percentages here, I'm plotting volatility in percentages, and this is exactly for the same set of assets that I showed you on the spreadsheet. When we are done with this module, I'm going to go back and show you how to do the same computation on the spreadsheet. I compute out what sigma R is going to be. It's going to be this number. And I'm going to plot this for all possible values of R. Notice on this slide, I'm plotting two different curves. One in blue, one is red. The red curve is not efficient. If you take a point here, this has a return of minus 2%. It has a volatility of, let's say, approximately 8%. We can get another portfolio with the same risk level, 8%, with much higher return. This particular portfolio up here has the same risk level, 8%, and has much higher return than this minus 2. So this entire red curve, in fact, is not efficient, and that's what it's been marked out. It says that it's inefficient. So why did we end up getting it? We ended up getting it because when we set up the optimization problem, we insisted that the target return should be exactly equal to the return that I specified. If I had made it greater than equal to, and you had specified a return minus 2, the optimization problem would have discovered that for that particular target return, the best risk is this 8%, but for the same 8%, I can give you a much higher return, and therefore this bottom line would never have appeared. The bottom line appeared only because of the equality constraints. It's sometimes convenient to put the equality constraints because we can solve the optimization problem simply, but later on we'll have to come back and then argue that certain parts of the curve cannot be efficient. All right, now I want to extend it to a D-asset problem and see how far can I push it. So here's the mean variance problem that I want to solve. Same thing, I want to minimize my variance, but now here's the expression for the variance. It's the covariance matrix sigma ij times xi and xj. I need to make sure that the x's that I consider is a portfolio, so the sum of the x's is equal to 1. And again, as before, instead of putting greater than equal to R here, I am putting equal to R for the same reason, because I have equality constraints and I can solve this more efficiently. In the prerequisite modules for nonlinear optimization, we had introduced this idea of Lagrange multipliers. The problem with this optimization problem is that it has two constraints, and I don't know how to deal with these constraints effectively. So the easiest way to do it is to construct something called the Lagrangian. And the way to construct the Lagrangian is to take the objective function. So this box here is just the objective function. Take the constraints. So this particular constraint is the target return constraint, except that the R, which was on the right-hand side, I set it equal to minus R inside the bracket. This constraint is the constraint that says that the sum of the x's should be equal to 1. That is, they must be a portfolio. And again, the 1 on the right-hand side, I moved it into the left-hand side with a minus 1. And then I multiply it by two multipliers, u and v, which are called the Lagrange multipliers. Now, having put the constraints into the objective by multiplying by the Lagrange multipliers, I'm going to completely ignore the constraints. I'm going to say that this is now an unconstrained problem. And we know that for the optimal solution of an unconstrained problem, we have to compute its gradient and set it equal to 0. Now, this particular objective function, assuming that u and v for the moment are just multipliers, they are not unknowns, the decision is in terms of these x's, and there are d different x's. So I have to take the partial derivative of this expression with respect to all of them and set it equal to 0. If you take the partial derivative with respect to I, you'll get 2 times sigma ij xj. That's the derivative that's coming from this term. You'll get v times mu I, which is the term that is coming from here, and minus u, which is the term that's coming from there. And I'll set it equal to 0. I'll have one equation for all i's going from 1 through d. So I get d equations from here. I have two other equations from here. I need to make sure that my portfolio satisfies the target return. And I need to make sure that it's a portfolio. So I have two equations here. I have d equations here. And how many unknowns do I have? I have actually d plus 2 unknowns. Why the extra 2 unknowns? The two Lagrange multipliers, u and v. So here are the original set of unknowns. Here are the new unknowns that I introduce. I have d plus 2 unknowns, d plus 2 equations. I can solve it. And in the next slide, I'll show you how to set up the linear equations to solve it. Here, I'm going to encapsulate this story into a theorem which says that a portfolio X is mean variance optimum if and only if it's feasible, it satisfies the constraints, and there exists U and V, multipliers U and V, which satisfy these constraints star, which satisfy all of these gradient conditions. And this will become important in a few slides. All right. So here, all I've done is I've taken these equations that are there, these D equations, and the extra two conditions on the portfolios and set them up as a one large matrix. So up here, all of these equations are the gradient equations. This equation is the target return equation. This equation is the portfolio equation. So there are D plus 2 equations here, D plus 2 unknowns. All these zeros corresponds to the gradient conditions that they must all be 0. This R is, of course, a target return. And this 1 is the fact that it's the portfolio 1. So that's some vector B. This is some, I'm just calling this matrix A. And we just simple linear algebra tells me that if I take all of these portfolios, this vector I can compute it by simply taking the inverse of A and multiplying it to this vector P. Done. In the rest of this module, what I want to do is give you a little bit more structure on what do these portfolios look like. Is there any interesting structural properties underneath, which we'll use later to derive something like the capital asset pricing model. So we're going to walk through a couple of slides, which will end up showing something called the two-fund theorem. The two-fund theorem says that the entire efficient frontier can be generated by just looking at two portfolios or two mutual funds. So suppose we fix two different target returns, R1 and R2, and I go and solve for the optimum solution for R1. What do I mean by solve for the optimum solution? I go to this set of equations, plug in R1 over here, and compute the optimum portfolio. That's optimum portfolio. I'm going to label it as X superscript 1. And when I solve for that portfolio, I'll also compute out the corresponding Lagrange multipliers V and U. I'm calling them in this slide V1 and U1. I'll take the other return R2, do the same thing. The optimum portfolio, I'm going to label it as X superscript 2, and the Lagrange multipliers and V2 and U2. Okay, now we take any other target return R that we want. I'm going to arbitrarily create for you another position Y and argue to you that this position Y in fact is the optimal solution for that new target return. And here's how it's going to be constructed. You take the target return, and you choose a number beta, which is R minus R1 divided by R2 minus R1. And if you remember back, in the two asset market, the X was simply R minus mu1 divided by mu2 minus mu1. So this should somehow give you an idea that we are going back slowly to this two asset market, which is effectively what this two fund theorem says. I'm going to create a new position Y. I don't know whether it's a portfolio for now. And the way I'm going to construct this Y is I'm going to take 1 minus beta times x1, which I know, and beta times x2. I'm going to add them up. This will give me some positions in all the D assets. And let's walk through and see what happens. So first thing that I'm going to do is compute out the sum of all the components of Y. Sum of this Yi's is nothing but 1 minus beta, the sum of the corresponding coefficients of x1, beta times the corresponding coefficients of x2. X1 is a portfolio, x2 is a portfolio, so this sum is equal to 1, that sum is equal to 1, 1 minus beta times 1 plus beta times 1, if you add it up, you get 1. So, after this calculation, we know that this Y, which was just a position right now, is now a portfolio. It's a set of numbers that adds up to 1. Now let's calculate out what is the expected return on this portfolio Y. That's mu I times yi. Expand it out again, it's 1 minus beta times mu I times x1i, summed from I equals 1 through d. Beta times the sum of mu I times x2i, summed from 1 is to d. This one, remember, x1 is feasible for a target return, so it's actually equal to R1. This quantity is feasible for a target return R2, so it's equal to R2. So it's 1 minus beta times R1 plus beta times R2. Plug in the value of beta that it was computed, you get exactly equal to R. And if you connect back to the the two asset case, this is exactly saying 1 minus x times mu1 plus x times mu2 must equal R, which is exactly the equation that we solved there. Now we are going to argue in the next slide that this y in fact is optimum. And how are we going to do that? I'm going to use the theorem which says that if I can find multipliers u and v for which the equations hold, then y must be optimal. Because y is feasible, it is a portfolio, it has the right target return. If I can find you multipliers such that all the gradient conditions hold, it must be the optimal portfolio. So I know v1 and v2. So I take a guess and say that the v variable corresponding to this new position is just the same multiplication. 1 minus beta times v1, beta times v2. 1 minus beta times u1, beta times u2 is going to be u. Here's my sigma ij, yij minus v mu I minus u. This is the gradient condition that corresponds to asset I. So this is the partial derivative of the Lagrangian with respect to the asset I. I plug in the values for what this is nothing but a plug-in for what yj is going to be. Here I'm plugging in my guess value of v. Here I'm plugging in my guess value of u. You rearrange term, take all the 1 minus beta terms together. You end up getting something that just depends on the asset 1, the multipliers v1 and mu1. But x1 was optimum, therefore all of this bracket must be equal to 0. Similarly, if you collect terms for beta, you'll get terms that correspond to x2. But x2 was optimal, so therefore this must be equal to 0. 1 minus beta times 0 plus beta times 0 gives you 0. So I have constructed for you multipliers v and u, such that all the gradient conditions hold. Therefore, y must be optimal for the target return R. And we have this theorem which says that all efficient portfolios, all the portfolios that are there on the efficient frontier can be constructed by diversifying between any two efficient portfolios with different expected returns. The only condition that we needed on x1 and x2 is that they have different returns. So everybody, whoever is going to be investing in this market, they're happy if I just give them two mutual funds and say, okay, you can just invest what you like on these two mutual funds. So why are there so many mutual funds in the market? There are over 6,000 of them floating around. Why are they there? You might want to pause your video here for a second and think about it. So the reason those different mutual funds are there is because we are assuming in the background here that all the investors have the same expected return mu and have the same covariance matrix sigma. What do I mean by they have? Meaning they estimate what is going to happen in the future by the same mean vector and the same covariance matrix. That's never going to be true. So even if they are all mean variance investors, they might have different estimates, which means that their efficient frontiers would look different, which means that a portfolio or a mutual fund which will be efficient for one investor may be completely inefficient for another investor. There's also no reason to believe that everybody is a mean variance investor. This is another topic that we're going to talk about towards the very end of this module. And so, although this theorem is very interesting and important and in fact led to the development of the mutual fund industry as a whole, you should take it with a grain of salt that there is a gap between what theory is and what practice is going to be. All right, returning back to the theory, the theorem says that all efficient portfolios will be constructed by diversifying between two efficient portfolios, which means effectively it's a two-asset market. If I'm talking about investors, they don't need anything more than two assets. And therefore, since y star can be written as a combination of x1 and x2, all I've done is rearrange terms. I took the r outside. I put x2 minus x1 divided by r2 minus r here. Call this a new position g. Call this a new position h. So therefore, every component can be written as r times gi plus hi. Plug it into the expression for variance, and you'll end up getting again that the efficient frontier has the same structure as the two-asset efficient frontier. And therefore, we'll just end this module by showing you that the efficient frontier looks the same. Again, the same story. This bottom is inefficient, and the reason we had this because instead of putting target greater than or equal to R, we set target equal to R. And this equal to ends up giving this the inefficient frontier at the bottom. And we'll stop.